It's a real pleasure for me today to be able to welcome Bob Dillmore from NETL and the Technical Director of the National Risk Assessment Partnership, or Nrap, to speak at the SMART webinar series today. Thanks to everyone for joining the discussion, but thanks to Bob. He's going to be talking about Nrap Phase 2, what the Nrap team has been doing. I know there's a lot of folks here who are at least somewhat, if not very familiar with Nrap, but I think this will be an excellent opportunity for the whole of the SMART team to hear what's been going on within Nrap and some of the connections and potential collaboration points within. So, without further ado, take it away, Bob.
Okay. Thank you, Grant. Thanks, everybody, for joining in, and I appreciate you taking the time. I will, as Grant said, give an overview of the work that Nrap has been doing over the past few years during its second phase of research. Probably will stop my video for the time being, if people don't mind, and I'll turn it back on at the end. There we go. Yeah, I have a pretty simple outline here. I'm going to try to give you an overview of the Nrap mission and the approach, just a tiny bit on the history of Nrap, and then talk about the Phase 2 products and what we're trying to accomplish in Phase 2, and then give my thoughts on where there may be areas of synergy with SMART and other work within the carbon storage program, and maybe just a few thoughts on possible future directions that I think would be valuable. Hopefully that this will be a good start for a discussion. I think, as Grant mentioned, there are already a number of people who are working in both SMART and Nrap. There are clearly synergies there, so hopefully we can use this as a jumping off point to discuss those more in the future. Let me move this window down here. The goal of Nrap is to leverage the capabilities from across the 5 contributing national labs to develop methods and tools to quantitatively assess and manage also the long-term environmental risks associated with geologic carbon storage in the context of the significant uncertainty and the variability that can exist at a site. And the two risks that we concern ourselves with are potential for unwanted fluid migration through the subsurface back to the atmosphere, and also potential for induced seismicity from large volume C2 injection. Again, the work, the research team is from 5 national labs, 5 of the SMART national labs, I think, NETL, Lawrence Berkeley, Los Alamos, Lawrence Livermore, and Pacific Northwest. This presentation, I think I mentioned, will be an overview. There is a lot more detail to go into. If there's specific questions that come up, I think we can point to some folks who may even be in the audience, but if there are questions that come up, certainly can direct you to other folks who may not be on the line who could help to answer this. The work we do is informed from input from a stakeholder group that includes, academics, state and federal regulators, industry folks, some NGOs, and other government agencies. And I think that really helps us to ensure that the work we're doing is relevant and impactful. So here's a picture of the Nrap team. The last time we were able to get together in person, which is quite a while ago at this point. We do still, though, meet regularly on web-based meetings, team meetings for individual tasks in the larger group. This is a picture from our last group meeting. It's sort of the Hollywood Squares version of Nrap. But looking forward to being able to meet everybody in person sometime again in the near future. So I think all of the work in the carbon storage program is kind of motivated by this overarching objective to get convergence between the CO2 capture technology and the readiness of carbon storage in this 2025 timeframe, which is, coming quickly, and to really move beyond that and ensure that commercial scale deployment is something that can be realized. So that was sort of the objective of the program all along. And in the new administration, I think there's been perhaps a reinvigoration or an emphasis on the value of carbon storage as it fits within the larger toolbox of energy technologies that will reduce emissions and hopefully get us to a net zero emission state in the not too distant future. But I think it's worth emphasizing this point on the right here from the Deputy Secretary from April that says that right now is really a make it or break it opportunity or window on the CCUS front, which is to say that this is technology that has been in development, I think in a very methodical and appropriate way by the carbon storage program over the past, couple of decades. But now, given the challenge of dramatically reducing emissions in a expedited time frame, there's really a need and an opportunity to bring these technologies to a deployment state as quickly as possible. And so in phase one of Nrap, we really tried to tackle this sort of simple question, which is just how big might the risks be from geologic carbon storage operation? There was already back in 2010 this conceptual cartoon of how the risks might evolve at a site, which is essentially that as injection begins, this is from Sally Benson, the risks will increase as the CO2, more CO2 is loaded into the subsurface system. After injection stops, the system will begin to relax, and the potential, for an unwanted condition will go down over time as the pressure stress condition in the system relaxes. But there really were never any quantification of either the time scale over which those risks would relax or the magnitude of the risks that might evolve. So and the spatial component as well. So this is really the challenge that Nrap in phase one took on, and over the course of this 6-year period, the group pioneered methods for quantifying the behavior of systems, not just the storage interval, but storage interval and the potential leakage pathways, the behavior of the faults and fractures, legacy wells in the system, and really develop, some early versions of reduced order modeling approaches that allowed for fast forecasting, and also an integrated assessment approach that allowed the integration of different components of the system. And the product of that was the first quantitative risk profiles, and then a set of tools. So just very generally, I'll say that the approach that Nrap took in phase one, and it's really the basis of what is continued and built upon in phase two, is that recognize that this is a complex engineered geologic system, and to characterize the behavior of the system as one comprehensive model, fully coupled model would be, especially at the time, I think it still is the case that it's computationally very, very expensive and potentially intractable, especially as you start to consider the uncertainties. So the approach that has been taken is to break the system up into its important components, the storage reservoir, the cap rock, the leakage pathways, the receptors of concern, and to develop either reduced order models. They're based on ensembles of detailed numerical simulations, or fast analytical models. Really use whatever approach is credible and makes the problem tractable to characterize the behavior of this different system components, and then couple those together in an integrated assessment framework and exercise that to understand the performance of the system in the context of the data, model, and scenario uncertainty. So then the product of that was a set of 10 tools that were released back in 2016. There was some recognition internationally for these tools. Also, the underpinning science that was published in a number of journals, but there was a virtual special issue that sort of highlighted several pieces of work from the Nrap Phase 1. So these are some of the outcomes. And I think, and again, the first quantitative risk profiles is an important aspect of this, risk of leakage back to the atmosphere, but also risk of related to seismicity and risk of impact to underground sources of drinking water. And then building upon that in Phase 2, now we're trying to understand, now that we can assess the risks quantitatively, how can the risks as they present themselves at sites be managed, and how can we use risk-based approaches to help inform stakeholder decisions that relate to, site selection, permitting at a site, and injection operations and closure. So really throughout the life cycle of the site. And so building upon this framework for characterizing the behavior of the engineered geologic system to develop quantitative risk profiles, now in Phase 2, we're building, I think, additional reduced order models for different system components. We're improving upon the reduced order models for the ones that we already have characterizations for. Unfortunately, I'm not going to go into excruciating detail about this today. I think there's just not enough time, but I think I give one or two examples here in a bit. But then building upon that core functionality, now we're applying this really fit-for-purpose approaches, methods, and the embodiment of those methods in codes that allow us to do fit-for-purpose analysis that really supports different stakeholder decisions as they're made throughout the life cycle of a project. Still at this site scale. Another important aspect of Phase 2 is that we're sort of redoubling our efforts now. I think that in addition to that formal stakeholder engagement through our stakeholder group, we're really trying to more actively engage with tool users for the Nrap tools, with industry stakeholders who have a lot of practical experience in how decisions are made at engineered geologic systems, with regulators who are tasked with evaluating the performance of system and the proposals for different CO2 storage operations. So this is sort of, this DevOps concept is sort of embedded in everything that we're doing in Phase 2, and I think increasingly through the Phase 2 period. So, and just the pyramid here on the left shows that foundational to everything we do is the research itself. In addition to the research, we're building computational tools that we think will be useful for stakeholders, protocols and workflows that apply the tools and concepts that we're developing to address questions that are important to stakeholders, and trying to get to key insights about the risks as they evolve at a site for a geologic carbon storage project and the acceptability of those risks. So just starting here at the base of the pyramid, I'll just give a couple examples after this. It's kind of a smattering, I apologize, but the In phase 2, we again have a virtual special issue of the International Journal of Greenhouse Gas Control that was released last September. I think that has 16 or 17 Nrap-related articles that are all brought together in one space. Certainly not the only place where we're publishing. We sort of target any relevant journal, but this is a good place to start if you're interested about learning about some of the recent Nrap research. We also are developing as sort of test cases. I think dummy problems is one term that's used, but I think these are a little bit more robust than what I would call a dummy test problem. Sort of a sandbox data set that allows us to do research quality analysis of the behavior of engineered geologic systems. So we're looking at the Kimberlina site in California and then the future Gen 2 site, neither of which have seen any CO2 injection. These are data sets that we have found very useful for the research that we do. We've also released them through the Energy Data Exchange. I think some aspects of these data sets have been used by the SMART group, as I understand it, and then you guys are building upon that to make those data sets sufficient quality resolution to do the kinds of analysis that you are interested in. So I think that's a fantastic win for the Nrap team that we're seeing, follow-on application, further development based on some of those data sets. These are statistics from our project's publication list, but I think it's not just the publications themselves, it's also the other products that we're building that need to be considered. So just a couple of examples related to well leakage, well integrity. Just to give you an idea, there is both experimental work that we're doing to resolve critical uncertainties about the performance of the system, in particular how stress in flow paths, residence times, and chemistry govern the permeability evolution of fractured cements in this case, and also numerical simulation on large ensembles of simulations that complement those experiments that try to constrain the important behavior that may affect the long-term integrity of wells as barriers to unwanted fluid migration. Also, there's data-driven work, so looking at surface casing vent flow, sustained casing pressure, from oil and gas wells from a number of states, trying to understand what that might tell us about the incidence rates and the correlated attributes of a site that may influence the long-term integrity. So this is just an example. Another example of some research, and I was trying to find a good way to summarize this. We're trying to use large ensembles of simulations with the physical response of the system to CO2 injection and potential leakage, both through wells and through faults, as the basis to do modeling of geophysical monitoring, and using, again, stochastic modeling of the geophysical monitoring response to understand what would be practically detectable at the surface or in some other monitoring deployment in order to detect with confidence that there is a leak at a site, so you can then respond to that observed leakage. So the approach, again, that we take is not a particular approach. We'll consider both full physics inversion approaches, also rapid prediction approaches. So I can't even remember what I put into this. I apologize. But okay, so there's an example of this is the the Kimberlina 1.2 data set. It's an ensemble of about 6,000 simulations of well leakage. Use that as the basis to model the geophysical monitoring and the direct temperature and pressure monitoring of for that leakage, and not for a single realization, but for the large ensemble of realizations, and then using that as the basis to estimate the practical detectability as a function of things like depth, salinity, the CO2 saturation, the size of the plume, et cetera. And so this is just kind of a cartoon that represents a large body of work. In addition to full physics inversion and that approach, there's also something that I think is much more closely aligned with what's going on in SMART, using deep learning inversion approaches, in this case of gravity monitoring, to understand the detectability of a plume and be able to discriminate plumes in different locations in the subsurface. And then this, there are lots of other work that I'm not talking about. This is just a cartoon to kind of show you that the idea then is to develop through test cases approaches to integrate our understanding of how the subsurface might behave with uncertainty, link that to not just the reservoir performance, but the behavior of the full system. Coupled to that, modeling of monitoring or estimations of detectability, and then use that all together in order to develop risk metrics that allow us to understand, things like what monitoring design is appropriate for a site, what mitigation approaches may be most effective at a site. So that is just a smattering of some of the underlying research. Jumping into the computational tools, we have developed, again, a set of phase 2 tools. Right now, I think we have six tools in the phase 2 tool set. These have all been released. They're all out there available on the NETL Energy Data Exchange. We continue to refine them until the end of phase 2, which I should have mentioned before is kind of March to June, maybe 2022 timeframe. And I'll go through, I think, these very quickly. In addition to improving the tools, we're also developing the documentation and test cases for the tools, doing quality assurance and benchmarking, which I think is important because we hear, in particular from our industry stakeholders, that without quality assurance and benchmarking, they really will not have the confidence that they need to start applying these tools to candidate carbon storage sites. Something I really wanted to make sure, I'm trying to advertise this now, we just developed a user forum for the Nrap tools. This is available through the Energy Data Exchange at the same location where the tools are accessed, the workspace where the tools are accessed. It does require that you have an EDX account. It requires that you have permission to access the Nrap tools. If anybody needs that, please just reach out to me. Reach out to nrap at netl.doe.gov. So there are a number of ways to contact us, but we're trying to get people to pose the questions about the tools or make comments about the tools that they might have made by email previously in the user forum so that everybody can benefit from the questions and from our responses to those questions. You'll see if you get into it that this actually has a lot of the functionality that a commercial forum might have. So I think we're pretty happy with it. We just want to get people to start using it so we can really use this as a good communication tool. So talking about the tools very quickly, I think the flagship tool is this Nrap open source integrated assessment model. So this is developed in Python. It's freely available. A lot of these fit-for-purpose functionalities that I mentioned before related to establishing a risk-based area of review, evaluating the plume stability. I'll talk about this a little bit more in a few slides. Evaluating an appropriate risk-based post-injection monitoring period before you can close the site. These sorts of analyses are all built in as code to the integrated assessment model. These are largely available as control files, so it does require some familiarity with Python. We are also working through this SBIR grant that was given to a company called Illinois Rockstar. They are building a commercial quality graphical user interface for the integrated assessment model. They recently finished their phase 1 SBIR, so that is a product that's not yet commercially available, but is in development, something that the program has invested in through the SBIR. And I'll maybe give a couple examples of that in a little bit. The induced seismicity related tools are three of them. The state of stress analysis tool has a Bayesian approach to quantifying the confidence in the current state of stress and where the state of stress may be in the future as a result of the perturbation of the system through CO2 loading, pore pressure increase. And so it's a framework that allows estimation of the probability density of the state of stress at a given point over time, and estimation of the potential that a critically oriented fault could be activated over a given range of pore pressures, which is the plot shown on the bottom there. And this is all based on the assumption that the fault is critically oriented, which is an extremely conservative approach. There continues to be development of this. There will be a new version of this tool before the end of phase 2. And we will be, of course, announcing that when it's available. The second tool is a short-term seismic forecasting tool. Again, I think there is a real-time seismic forecasting tool that's more of a data-driven approach that's being developed in the context of the SMART project. This is sort of the predecessor to that. It's based on a little bit more of a physics-based approach. It uses an assumption of in its current state, an epidemic-type aftershock model, and uses catalogs of prior seismic history at a site and the current new injection activity as the basis to do this very short-term, on the order of hours to a couple of days, forecasting of what the future seismicity might be at the site. So that is complementary to what a stoplight type approach that is currently described and used by industry, I think, and is applied in things like Class 6 permit applications related to emergency and remedial response plans. The last here is the seismic risk, probabilistic seismic risk analysis tool called the RiskCat. It's really an integrated assessment model for new seismicity. This, I think, requires a little bit more focused expertise as a seismologist and or seismic risk evaluator to use, but it is available. All these tools are available through the EDX or through a Git repository. Again, this is an embodiment of this probabilistic seismic risk analysis approach. It incorporates aspects of seismic source characterization, predicting the ground motion at the site, the felt seismicity at the Earth's surface, estimating the hazard associated with that, and for example, the structural vulnerability of the built environment. There are fragility indices that are able to incorporate in here and develop risk estimations based on those things. The monitoring tools, two monitoring tools that have been developed in the course of phase 2 are the DREAM tool, which you might be familiar with, designed for risk evaluation and management. This is, and I think I have another slide on this in a minute, and the other is a passive seismic monitoring tool. These are both using optimization approaches. The first, the DREAM tool, is it's there to design what the most efficient and effective monitoring of the site might be. So it's an optimization that considers minimizing the cost associated with monitoring and minimizing the time to first detection, which is essentially equivalent to maximizing the probability of detection. And so it considers combinations of sensor deployments in order to detect potential unwanted fluid migration, and kind of uses a simulated annealing approach and to move the sensors around to find the optimal design. Historically, it was used for things like groundwater composition monitoring. Then electrical resistivity tomography was added early in phase 2, I believe, of Nrap, and now there's gravity has been added. There's some generic spoke surface and downhole arrays that are accommodated, and it really finds the optimal monitoring design based on the constraints of the system, which may relate to costs, may relate to physical locations where you can monitor versus where you are prohibited from monitoring. Considers trade-offs related to cost and time to detection. The passive seismic monitoring tool also uses simulated annealing. Superstructure for the superstructure for this optimization is very different, though. It's trying to maximize the detectability of some attribute of the system in a targeted monitoring location based on the distribution of a geophone array, which could be at the surface and or downhole in this example, which I think is for the Farnsworth site. I don't have that shown here, sorry. Just the number of surface seismic stations that are required is determined based on the standard deviation of the error plot. And when you start to get a drop in the error, you assume that I think the assumption is that the optimal design will be there where that turning point or inflection point for this curve exists, and that sort of gives you information about what optimal monitoring the minimum number of sensors might be. The tools and also the methods that the recommended practices that I'll talk about in a bit are all being validated to the extent that we have data and information available to validate them. Sometimes we use real field data. Sometimes we use analog sites. Sometimes we use hypothetical sites, simulation-based sandbox problems like we were talking about earlier. And I'm not going to go into this at all, but we do have a catalog that we've published on our website and through the Energy Data Exchange, where you can get a summary view of all of these applications and also links to publications that are describe them in much more detail. Moving up on our pyramid, we have recommended practices for risk management that I think are an important newer development for the Nrap Phase 2. So this is really based on feedback that we got from the stakeholder group, from our executive committee, that just putting the tools out is really not sufficient, even with some examples. We really need to spell out a coherent conceptualization of how a risk-based approach can be applied at a site to better inform the decisions that stakeholders need to make. So the approach that we took was to develop something that it's relatively conceptual in its representation. We didn't want to prescribe the Nrap tools had to be used to address these different workflows within these recommended practices, but we really wanted to lay out the thought process that we thought was appropriate that tackled each of these important steps or workflows within a larger recommended practice. And we have two of these. One is for new seismicity and one is for leakage risk. Both of these were released back in March. We've been eliciting feedback in a very general way. We asked through the carbon storage newsletter, maybe 2,000 people, 1,500, 2,000 people to review it and give us feedback. We've also, reached out for specific sections and asked subject matter experts for their opinion. We still are accepting feedback, although we're getting closer to a phase where we're going to update and then hopefully issue final recommended practices documents here in the next few months. We still would be very interested. If anybody has any feedback, please reach out to me if you need access to these. I think we have, for example, the link here just shows you the link to the current version that's out for review. you just want to talk through it, we'd be happy to sit with you and present the framework. So in the very general overview, there's some pre-injection, a priori risk assessment based on best available information at the site. So there's a site characterization aspect of this, both of the features, events, and processes of the physical system, but also the initial state of stress and how that state of stress may evolve over time. And then assessing the risk-based area of review. This relates to decisions that are made relative to a Class 6 permit application. Strategic monitoring, initial design at the site, understanding, developing the first assessments of the performance of the system, so that when you get observational data over time, you can update that understanding. You can evaluate how well the forecast of the system is forecasting as compared to the observational data at the site. And then, as I discussed very briefly before, evaluating different mitigation scenarios and evaluating, developing justifications for how long you would need to monitor a site after the site closes. So there's an initial characterization and then some periodic updating based on new information, new observations of the behavior of the system. So that's sort of the conceptualization. There is another parallel induced seismicity risk management protocol that's also available. I'm going to move past that because I think I'm taking probably a little bit too long. Let me check my time here. Yeah, I think I can finish in the next 5 or 7 minutes. Just to give a couple of examples about some of these workflows, fit-for-purpose workflows that we think support decision-making at a site. So on the left here, this is a picture that's from the Chadwick and Noy 2015 paper. It really brought forth this concept of conformance of the carbon storage site with, and I think Nrap has done a lot of work to nail down a little bit of the conceptual basis for what conformance actually means. I'm not going to go into detail about that, but it's a combination of, is the performance of the carbon storage system acceptable, given engineering constraints, regulatory constraints, and is in addition to the acceptability of performance, is the behavior of the system matching closely enough with what was forecasted to behave, the system behavior to be. So if it's really behaving in a way that's totally unlike what you expected, then I think you really need to stop and decide if you need to better characterize the system before you proceed, or proceed but monitor the system a little bit differently. So there's some work that we've done to bring this concept of conformance assessment into a quantitative basis. This is, again, a Bayesian approach that uses observations at a site. You have a prior understanding of what the site behavior may be, what the features, events, and processes of the system might be. You characterize those as best you can. For example, here with a variable porosity and permeability field in the storage reservoir, then you start to collect observations at the site, and you use those observations to update your model of the system. And then you can see here, in the case of saturation of CO2 in the subsurface in the storage interval, the observations allow you to dramatically constrain that uncertainty and really increase your confidence that you have good conformance and that you understand the behavior of the system, and essentially improving stakeholder confidence to enable future decisions. Another example is, we have stochastic representations of the reservoir behavior in a system. We can use that to understand how the plume will evolve over time and how that plume will stabilize. We can then apply the integrated assessment model to characterize the risk associated with that. So we understand how the plume will evolve, the dynamics of the plume. We also understand the risk evolution. And we can use so this was embedded in the integrated assessment model, a robustness uncertainty quantification approach in order to say, given the uncertainty at the in the plume behavior, how robust is our assessment of the conformance of the system given the uncertainty? So I might have jumbled that a bit, but it allows us to understand with the confidence that we have in the behavior of the system. Something that's a little bit more tangible, an important aspect of the Class 6 permit application is an area of review for a site that's initially overpressured. The analysis of what the area of review is becomes a little bit tricky, and so we advocate in some of the work from Diana Bacon and colleagues that you can use the integrated assessment model, account for the uncertainty in the reservoir, the uncertainty in the leakage pathways, in order to, and also the receptors of concern, in this case the groundwater, to understand what the leakage to the groundwater would be, but also the detectability of that leakage, whether or not that, I'm sorry, not the detectability, but whether or not that would cause a change in the composition of the USDW groundwater that would increase above a no detection threshold. And the argument is if it's not detectable, if it's so small that it's not detectable, then it should not be considered a concern for area of review. And so this risk-based approach really sort of presents a pathway to do this analysis for a site that's initially overpressured. And in this example case, which is the Future Gen 2 site, a hypothetical site, so you can, in this case, make an analysis that builds a justification for a reduced area of review based on, as compared to what was approved in the Class 6 permit for that site. Another example of an application of the integrated assessment model is coupled, in this case, with the DREAM tool, which is the monitoring design optimization tool. So we can characterize, again, the reservoir performance, the leakage to overlying receptors of concern, and intermediate formations. So these are intermediate formations, are not necessarily groundwater. They're not groundwater formations, but they're just potentially formations that you could monitor and detect fluid migration in. And you can run an ensemble simulation. You then apply that and the fluid migration to these intermediate formations in USDW as the basis for running the DREAM tool to determine an optimal monitoring design, so then you can assess your time to detection. And then, given the set of stochastic scenarios that have been considered at the site, you can develop essentially a distribution of the time to detection if there were to be a leak. And so, in this case, you can see that the detectability of a leak would occur in the vast majority of cases before injection operations were over. So, and post-injection, there's just some realizations that fall within the first 5 years or so, where you could see fluid migration after injection stops. So this is 5 years post-injection as compared to the 50-year post-injection, which is approved for the HIS period, which was approved for the Future Gen 2 Class 6 permit. So if you double this time, just to add a factor of safety and say you have 10 years of post-injection period, you're going to eliminate the need for 40 years of post-injection monitoring and can really have a risk-based justification for that. You could avoid a substantial cost for monitoring at the site. So all of this to say, we see this accelerated interest in deployment. Yeah. Please. Hello?
Keep going, Bob.
Okay, sorry. So yeah, we see an accelerated interest in deployment, increased potential for large-scale deployment. In the near future, I think we're really trying to hone the message, and now and going forward, that the Nrap approach, methods, tools, recommended practices can help stakeholders to reduce the uncertainty, which ties to the liability and decision-making costs associated with development of the site. It can expedite the permitting process. Even if it's the conceptual approaches, we think that, and not specifically the Nrap tools, we think that these tools and approaches do add value for stakeholders, and we hope that they help expedite decision-making, reduce uncertainty, reduce cost. We understand that the work that we were doing at Nrap is in the broader context, both of all the other great work that's going on in the carbon storage program, also industry work, the international research, development, and deployment community, state, federal regulators, really are trying to do that DevOps thing that I described earlier and make sure that our work is relevant and complementary to the other work that's going on, and we find those synergies where we can. This is sort of a simple, it doesn't capture all those elements, but between Nrap, SMART, and the large demonstration projects that the program has, we really see that there's opportunity to leverage all of these tools and capabilities to expedite and help validate models to support rapid permitting and deployment of carbon storage. My last slide here, I will just say that pretty much everything we've done in Nrap has been at the individual project, at the site scale. If indeed we are going to scale up rapidly to gigaton scale storage, then we will see lots of projects going in within a single basin. I think there are questions about how that deployment should occur to maximize the storage potential, to minimize the risks, to accomplish the goals of the administration and just effectively implement carbon storage technology. So what are those risks associated with rapid basin scale deployments? I think that still needs to be, still more work to assess those things. And then after they're assessed, if they prove to be worth looking at more, then how can you quantitatively assess those? How can you manage those? I think leveraging some of the approaches that we've developed in Nrap. That's all I have. I'll stop and see if there are questions.
Thanks, Bob. I'll open it up for questions to anyone.
Hey, Bob, I put one in your chat. I don't know if you saw it. I sent it just to you. This is Dave Sircone, so I'll just tell it to you. I'm an oil and gas guy, so Nrap's really not my specialty. However, with some experience previously coming to DOE, I worked in the energy industry, and I worked in environmental consulting on, plume, nature and extent of plumes and dynamic modeling, all those things. And what I know is there's always some leakage of, the undesirable product. In this case, it would be the CO2. However, at the beginning, it's kind of a nuisance leakage rate, and then, it becomes a much bigger issue. But there's always some allowability for leakage, because if you don't allow some leakage, you're always building new facilities and pipelines to deal with, for lack of a better term, virgin reservoir. And so my question to you is this illegal line of thinking, or is it unreasonable, to allow, some leakage so that you can utilize your reservoir to the maximum?
Yeah. I think I understand the question. I think it depends on the perspective and who you are. If you are looking at MBA, if you will, for something like a 45Q tax credit, then that does allow for some leakage and what they call recapture of credits. So essentially paying back for the credits that you took, and then there was leakage beyond what you expected. So I think that is more of an accounting exercise, and that is acceptable in that circumstance. My understanding, and I'm not a regulator, but my understanding of the Class 6 regulation, and I'm sorry, the UIC regulations for groundwater protection is that there is essentially not tolerance of leakage to USDWs, to endangerment of USDWs. And I'm not sure what the latest interpretation of that is by subject matter experts, but and so those are two different perspectives. From the Nrap perspective, I would say that this is an important question to have the tools to address probabilistically in a way that's site-specific and can accommodate the appropriate physics and chemistry of the system. So, you know, and if there will be fluid migration, then understanding that it can happen, designing monitoring appropriately so that you can detect and appropriately, you know, respond to that, mitigate, is what needs to be done.
Right, because you can't, I mean, if you have the thou shalt not type commandments over all of this carbon CO2 capture, you would think that, you know, it's not going to really be, you know, widespread adopted because it's too difficult to, you know, do economically. You know, there has to be a balance between, you know, leakage / environmental protection and, you know, cost effectiveness. So just my 2 cents. That's all.
Well, thanks for the question. I do see a couple more questions here in the chat, so I'm going to try to get through some of them. Thanks, Veronica, for helping out with this. I think the next one is, going forward, is there still a role for companion tools such as fault flow, seal flux, seal fracs, and the end sealer, or are these subsumed by OpenIAM? So I think Veronica, I will try to paraphrase her answer, which is that the new integrated assessment model does bring in the seal, fractured seal leakage code. It brings in a new analytical model for fault leakage. There is a new, this is the thing I didn't get enough chance to talk about. There's a new reducer modeling approach that's based on ensembles of simulations of fault leakage that Los Alamos is developing. That will be incorporated into the integrated assessment model. So, and some of those tools, the seal ROM is still a standalone tool. There is a standalone fault ROM, but I think those are best applied within the context of the integrated assessment model to make sure that they're being applied coherently with the rest of the system model. Hopefully that was a good enough answer for that. And if there are more questions about that, please do follow up with Ernest Lindner, with me, with Veronica. I think we can get you a little more detailed responses on those. How does the current risk management approach handle hidden fault seismic risk and uncertainty arising from heterogeneity? So I think this is a big question. I won't attempt to tackle it, but I do think if you look at the recommended practices for induced seismicity risk management, it pretty methodically treats all of these issues, and it also sort of lays plain when those issues remain, you know, important areas for continued research. I think this Goldilocks sort of faults, that it's not so big that it's easy to delineate, with monitoring technologies, but it's not so small that it's not a induced seismicity concern is an important thing. I will leave that probably as a discussion for another time, and we can definitely follow up with Josh White and the rest of that task team. Well, hopefully the GUI will be available by the end of the month. So Veronica is saying this. I think there is some GUI that the research team has developed. It's not necessarily our forte. I think our capability our time is best spent developing the capability, the functionality of the integrated assessment model, especially now that there has been an SBIR that's working on a commercial quality GUI. We're really focusing more on making sure the model functions as it should. To streamline, can we try to decouple the site-specific induced seismicity risk from operational related parameters? I don't know, is Josh on? He may wish to address that, or anybody else from the induced seismicity team?
I am on. I can't see the question though. Maybe someone could clarify.
Yeah, maybe I can elaborate. That's my question. This is Fred Anazadeh. So in many of these projects that we work on, we focus on a particular site, and then we see, okay, what are the seismic risk factors? So if we can come up with a module that separates the site-specific risk factors from operational risk factors, then we might be able to do this whole permitting or transporting the concept from one site to another much faster and easier. So that's really my question. Because a lot of cases, induced seismicity is very much dependent on two different things. One is the site, and one is how you are injecting things and how you are basically different types of rates of injection and other factors. So how can we decouple these things so that once we have a module that works with one site, can also be transported to the other site if you just replace that module that is dependent on that particular site?
Yeah, so I'm just going to say before we've hit 3 o'clock, so I'll leave this sort of channel open. I have to jump off, but Bob, you can go ahead. Please finish to answer that question, and others who want to stay on can. But I do want to thank Bob for an excellent presentation. A lot of work that's been going on in Nrap, and looking forward to how we can make the most of what each other's doing as we move forward together.
Thanks for having me. I know that
Fred, maybe the short answer to your question is just there's an intimate combination between site-specific risks and operation choices, and I think we could have an hour-long conversation about that. There are a lot of nuances.
Maybe actually I would like to, I have some ideas, especially how we can combine some of the efforts of Nrap and SMART, and maybe I can have separate discussion with Bob and others on this.
Perfect.
Very good. Thank you.
Yep.
It was a great talk.
Well, thank you. Yeah, I do think that kind of thinking sounds very useful, especially as we start to move to basin scale deployment and thinking about de-risking at the basin scale. Are there important generalizations that can be made or that allow us to de-risk not just a single operation, but a class of operations that have similar characteristics? That sort of thing, I think, is very valuable.
Very good.
So I know several people are moving off to another 3 o'clock call. I am happy to stay on, but or talk separately with anybody who's interested.
Unfortunately, I have to move to the same talk, so I'll talk to you later. Thank you.
Okay. The question about cost here, I will address real very quickly. I think we have done some very preliminary work. So first of all, the DREAM tool does incorporate cost as one of the optimization criteria. We've also done some preliminary work to look at applications of some of the Nrap modeling of leakage with the cost model that the carbon storage program has developed for saline storage. I think that there is definitely more work to do there. I'm of the opinion that would be valuable for the program, especially as we move to deployment and making decisions that are not just risk-based, as we might consider them, but risk and cost, and maximizing injectivity in storage. I see one more question about improving conformance of models, predictions, and data, and the data aspects. For example, data diversity and anomalies. Have you considered? So I'm not sure I completely understand that question. I think the Bayesian approach that has been applied by Lin Chen and colleagues does, it's based on an ensemble of simulations which has assumptions built into it about how the system will behave, but then it uses real observations. So I think if there's an anomaly and the behavior falls outside of that ensemble of simulations, I think we'd have to ask Len to be sure, but I think it may cause you to revisit your initial ensemble of simulations and the parameter assumptions. So it still would be an updating step, but I think it may trigger a little bit more aggressive updating of the characterization of features and then some processes associated with the system. But I think it's an interesting question. Okay, well, thanks everybody very much for listening in. And again, I'd be happy to chat with anybody anytime. So just give me a call or send me an email at this address shown here.
Thank you.
Thank you.